Hi everyone, I'm Mafalda Ferreira. I'm from the University of Lisbon in Portugal, and today I'm going to talk a bit about our work on efficient static vulnerability analysis for JavaScript using multiversion dependency graphs. So Node.js is a runtime environment that runs JavaScript on the server side. It is part of popular full-stack frameworks such as Mellon and Limin, and it has also been adopted by many high-profile companies such as Netflix and PayPal. In fact, according to the 2023 Stack Overflow Developer Survey, it is the most used web technology by developers. Node.js applications rely on a high number of third-party packages, which are mainly developed and shared by other developers. This package ecosystem, the Node Package Manager, NPM for short, currently offers more than 2.5 million packages for developers. However, as there's no prior verification before developers can publish these packages, these packages are often vulnerable. So let's look at an example of a critical vulnerability in a Node.js application, specifically a command injection. So here we have a git reset function, which is designed to revert a Git repository to a previous commit. And this function is exported by the package, and so its parameters can be controlled by an attacker from the outside. And we call these sources. In line 7, we have a call to the exec function, and this function will launch a shell process that will execute the given command, and we call this a sync. In this application, this call depends on the values of options command and options commit, which are properties of the options object. And this object is defined here in line 4 as a sub-object of the config object. And so we can see that by using a malicious config, an attacker is able to manipulate the value that will reach the sync and execute an arbitrary command. For instance, if an attacker uses the following configuration, it will be able to delete all files in the server. So to have secure Node.js applications, it is crucial that we have tools that help us detect these types of vulnerabilities. In our work, we focus on these 4 vulnerabilities: prototype pollution, command injection, code execution, and path reversal. So to help uncover these vulnerabilities, static analysis tools based on code property graphs have become increasingly popular over the last years. And this approach divides the analysis in 2 stages. So first we have the graph construction stage, in which it will build a graph representation of the given package, which we name the code property graph. And this code property graph includes 3 different types of program representations, namely the abstract syntax tree, the control flow graph, and the program dependence graph. Then, in a second stage, the tool will query the graph in search for patterns that may indicate potential vulnerabilities. For example, command injection or prototype pollution. The main advantage of these tools is that the search patterns are entirely customizable through the graph traversal in the second stage, and so this offers high flexibility in detecting different types of vulnerabilities. Even with the advances in CPGs, a fundamental challenge that remains is deciding how much information should we add to them so that the definition and the identification of these patterns is straightforward and precise. On the one hand, with more information, we have richer graphs, which allow for more precise vulnerability patterns. But the queries, this makes the queries very complex to specify and later identify, and it also worsens the performance. On the other hand, if we have less information, we have simpler graphs, which will improve the performance, but will limit the expressiveness of the patterns that we can search for. And so a fundamental challenge in using CPGs is actually figuring out where's the sweet spot of the information that we should add. Currently, ODGen, which is the state-of-the-art tool for vulnerability detection in Node.js packages, extends this concept of code property graphs with what they call the object dependence graph to model JavaScript objects. And although very precise, ODGen actually suffers from performance problems. In fact, ODGen is not able to finish the analysis in many cases, which causes it to miss vulnerabilities. So in this work, we set ourselves to improve this performance without losing precision. And how do we achieve this? So basically, we do this by, instead of including all of those program representations that ODGen includes, we rely on a single graph that models the evolution of the objects and their properties during program execution. And we call them multiversion dependency graphs. We also implemented GraphJS, which is a vulnerability scanner for NPM packages based on these MDGs. And our evaluation shows that we are able to analyze 37% more packages than ODGen and actually detect 63% more vulnerabilities without losing precision. So in sum, our graphs are smaller because they rely on a single and simplified structure. And because of this, they allow for simpler queries because they only need to iterate through a single structure without going back and forth all of those program representations, looking for syntax and flow information. The construction algorithm is also formalized and proven sound. So our multiversion dependency graphs encompass two existing analysis techniques. So they have shape analysis, where the objects are mapped to the properties that they have during program execution. So here, B represents property P of object A. And also dependency analysis, where the objects and values are mapped to the values that they depend on. So here, C depends on the values of A and B. And our novelty is that in the same graph, we also keep track of the data flows and execution order using version information. Specifically, we create new versions of objects anytime the object or its properties are updated. For instance, here, A1 is a new version of A0, which resulted from a write operation in property P. And with this information is where we avoid going back and forth between all of those program representations. This simplification is extremely useful when detecting, for example, prototype pollution vulnerabilities, which need to take into consideration subsequent writes into the prototype chain. So let's see how we build the multiversion dependency graph for the example that I showed you earlier. And for this talk, I'm only going to focus on the structure of the objects, leaving out the dependencies, but you can find the algorithm in the paper. So first, we are going to add an object for each function parameter, which are going to be the sources. In line 4, we have a dynamic property lookup, and so we will add the options node to represent the property of objects the object config. In lines 5 and 6, we have two property writes, which are represented by the consequent version edges on the graph. And then in line 7, we have a node to represent the call to the exec function, which is the sync. And it depends on the values of options.command and options.commit. So by looking here at this single graph, we can already identify the pattern. So options.commit is a property of the options object, which is a property of the config object, which is controllable by an attacker. And essentially, the main insight of our multiversion dependency graphs is that they capture how the objects evolve over time as its properties are looked up and updated. To evaluate the effectiveness of these multiversion dependency graphs, we built GraphJS, which is an MDG-based static vulnerability scanner to analyze vulnerabilities in Node.js applications. And it follows the same structure of the code property graph-based tools. In particular, GraphJS detects the command injection, prototype pollution, code execution, and path traversal vulnerabilities. We used Neo4j as the graph database, and we implemented the queries using Cypher. And the queries are very simple. They are entirely customizable, and they can also be extended to support other things. Our evaluation focused mainly on answering these three questions. So how good is GraphJS in detecting these vulnerabilities? What are the performance gains? And can we actually find new security vulnerabilities? For this talk, I'm only going to focus on the first two. And to answer this question, we leverage two datasets from prior work, Vulkan and SecBench, which we use as our ground truth datasets. And combined, these two datasets provide a comprehensive set of vulnerabilities, 603, with the distribution summarized here on this table. These datasets are representative of real-world vulnerabilities, but they also contain a great deal of non-vulnerable sinks, which allow us to measure the precision of our tool. So to assess GraphJS's effectiveness in detecting vulnerabilities, we ran both tools, GraphJS and ODGen, in our ground truth datasets. We measured the recall in the first column and also the precision in the second column. And of course, the higher both values, the better. By looking at this table, we can see that GraphJS was able to detect 82% of the reported vulnerabilities, which is 63% more than ODGen, which only detected half of them. And we can also see a big improvement in the prototype pollution vulnerability, which is largely due to the fact that since we are building simpler graphs, we were able to finish the analysis more times and therefore find these vulnerabilities. To measure GraphJS's performance, we first measured the time that each tool took to analyze a package. And here is the cumulative distribution function of the time that, to finish the analysis. By the 10 seconds mark, we can see that GraphJS was able to analyze 95% of the packages, where ODGen flatlines at 70%. And therefore, GraphJS was able to analyze 37% more packages than ODGen. Of course, we also measured the size of the graphs generated by both tools. So in the first row, we have the size of the graphs generated by GraphJS, our multiversion dependency graphs. And in the second row, we have the size of the graphs generated by ODGen. We can see that the multiversion graphs are smaller than the graphs generated by ODGen. We only have 14% of the nodes and 42% of the edges. So there are many things that I did not cover in this talk, such as the full syntax of the graphs, the formalization of the analysis, and the soundness guarantees. But I invite you to read the paper to learn more about those details. So to conclude, I presented you multiversion dependency graphs, which is a new point in the design space in the code property graphs for JavaScript vulnerability detection. These multiversion dependency graphs are simpler. They have formal semantics, and they allow for simpler and more efficient queries. With GraphJS, we were also able to identify 49 previously undiscovered vulnerabilities, which actually resulted in 3 CVEs. And so with that, I finish my talk, and I'm ready for questions. Right. Thank you.
Questions, come up.
Hello, thank you. Very interesting talk. I was just wondering if you could elaborate a bit more on the security properties you're checking, because the example that you provided, you could do this with a PDG alone, given that your taint abstraction or your data flow abstraction is sufficiently precise, either through access path if you just denote a JavaScript object as base object plus fields, or using collection modeling if you constructed map style. So I was wondering whether you have an example where you really show that you need the versions and what the cool thing about the versions is.
So actually, the example that I show is more complex. I only show the taint side vulnerability for the sake of the talk, but in the example, we actually also detect a prototype pollution vulnerability. And to detect this prototype pollution vulnerability, we really need these version edges because we need 2 subsequent writes in the prototype chain. And so here we can see that, for example, we have a new version of the options with a property. And then we also have a new version of this new object with another property. Actually, I think it's missing. Oh, no, yeah, that's right. And so if we don't have these version edges, what we needed to do is to go back to the program dependence graph and see what were the objects involved in this pattern and see the order of the operations, and then we needed also to check the syntax. And so the queries are actually very complex because they need to go back and forth all of those program structures. And here we only need to do one graph traversal.
I wonder if you have a normal data flow analysis that is flow sensitive, and for that one, where you just look at the command execution, that should be enough, I guess, if I'm not missing anything. If you're talking about prototype pollution, then I wonder if your data flow abstraction is precise enough and your analysis is flow sensitive, then you should not necessarily have to go back and forth, maybe aside from aliasing.
I mean, if I understand correctly the question, if you look at the multiversion dependency graph, it's pretty obvious that the options.commit is a property of options, which is a property of config. But for example, if you rely on the abstract syntax tree, you need to reconstruct this structure at the same time as you're seeing the dependencies. So it's a bit more complex.
I'm talking about a monotonous framework you just propagate forward.
Okay, more discussion on this point will follow. We have a long list of people behind. There's time after the session, please.
Hi, thank you. It was an excellent talk. I'm wondering how you handle function calls, in particular higher order functions, like functions get passed around a lot in JavaScript. I was curious how your representation and framework handles that.
So we leave most of that logic to the query stage, where we are able to reason about function calls and the interprocedural aspect of the analysis. Here we mainly have the nodes for the calls and associated with the arguments that they have.
Okay, we can take it offline. Thank you.
Thank you for the nice talk. I'm a little curious about what's your threat model what you use when you collect the data set on the real-world NPM packages, and what's the entry point you want to use to start this analysis like path travel. So even you think the exported functions as an entry point, there are still some functions like the functionality is just running some command or just perform some circle queries, such as some circle drivers. So how you can just query to say there's a path from the parameter to the thing, but the function functionality is just do the stuff.
So are you asking like if the package offers that as a functionality?
Yeah.
Yeah. So when we analyze the reports on the real-world data set, and we check them manually. So first we checked whether there are true or false positives with manual exploits, and we excluded the ones that were the intended functionality of the package. So I actually have here a table. Yeah. So for example, we found 101 exploitable vulnerabilities, but only 49 of them were unreported and not an intended functionality of the package. But we needed to do that manually. We don't know the domain.
Okay, thanks.
Thank you. That was a great talk. I was curious about so you detect 82%. Is there a pattern on the vulnerabilities that you don't detect? Is there like a specific kind of complicated structure that the analysis misses?
I mean, most of the things were JavaScript things that we didn't, I don't know the word. We didn't put them in the graph, so we haven't modeled them. For example, since these applications rely on third-party packages, that there are packages that iterate the objects for you, and so we don't have that logic in the code. We don't do inter-package analysis, and so we lose a bit of that information.
Thank you.
All right, thanks again.